All right, welcome everyone. You should be able to see and hear me. Let's see if we can get you some slides as well. And there we go. So we're all set up. Welcome to the DevDays conference. I'm Philippe Ryck. I'm from Belgium. I used to travel to a lot of events to talk about security, and these days I do that from home, which is, well, let's say different. So that's definitely one thing. All right, so you're here. Which kind of means you want to learn something about API authentication, hopefully, or you ended up here because of a mistake, which is also perfectly fine. In that case, you're going to learn something about API authentication. So to put things straight before we really dive into some technical details in a couple of minutes, I want to make sure that we're on the same page about authentication and authorization. So one of the first things to realize is authentication is about providing proof that a party or an entity is who they claim to be. And there's all types of authentication because there's all types of other entities and so on and so on. But in the end, it basically means that you verify that someone is who they claim to be. And someone can be a human-based life form. It can be a piece of software, a service, something like that. Nobody really cares about authentication. In essence, authentication is just a means to an end, and the end, in most cases, or in virtually all cases, will be authorization. In the end, you want to make authorization decisions. You want to make sure that something or a certain level of access or certain operations or whatever is actually allowed. And to decide if something is allowed, you typically need to know who the other party is, at least some rough idea, so that you can make an accurate authorization decision. And that's essentially what authentication is typically used for. In this session, I'm not going to talk about authorization because we're going to focus on how to authenticate. We're going to go from simple mechanisms to more advanced mechanisms, basically. And just to make this a bit more tangible, I have an overview image of what this would mean in an architecture. So typically, you have a client application accessing an API. That's a very common setup. That's systems that we all build, that I build for customers as well, and stuff like that. But you usually have a couple of different clients, which can be server-side applications, mobile apps, desktop applications. There's a whole bunch of different types of clients with different requirements as well. On the API side, I wish things were simple, like we have one API, but in reality, we have a lot of APIs. That's already one change or one evolution of the last 15 to 20 years. And of course, today we not only have one type or one system with APIs, we have a bunch of other APIs as well who call each other and so on and so on. And when one API calls another, you can kind of make an abstraction of that image because it's the same scenario as a client calling an API. When when one of the group of 3 APIs calls the other API on the right side, it's basically a client calling an API. Sure, we call both of them APIs, but one acts as the client, one acts as the receiver of that call. And that's a very important distinction because that means, or a very important concept, because it means that this client authentication or API authentication applies within a server-side architecture as well. Clients often run on user machines, which will be a bit of a different story because, first of all, clients running on user machines run in an untrusted environment because we don't really trust our users as security people. So that's one change. And we typically also want to know who the user is, which brings us into the realm of user authentication, which we'll dive a bit or very briefly into at the end of this session. Service to service, or M2M, or whatever, app to app or API to API communication, that also typically relies on client auth. And I'm going to use some practical examples throughout this session. All right, the session is called Recipes for API Authentication because I'm actually a chef. I went to school, evening school, to become a professional chef. So that's one thing. And I kind of like food. So I want to tie things in with food. And I actually have some recipe cards throughout the presentation about API authentication. So don't get your hopes up too much. But we're going to talk about very simple things that actually work really well. Like this slice of pizza, New York style, very cheap, very probably not too healthy, but it's, we all know this kind of food, right? It's delicious. We like it. It gets you fed, and we're happy with that. Of course, sometimes you want to go something fancier. back when you used to be able to travel, you could go to Barcelona. So if you live there, good for you. Otherwise, you could go to fancy restaurants like that, which is definitely worth the experience. And sometimes you also find things that you wish you never saw. There's a great subreddit for that called shitty food porn, which will give you nightmares if you look at food like that. We're going to talk about each of these three types of API authentication as well. So we'll get to that in a second. Just a small word about me. I'm Philippe Ryck. Like I said, from Belgium. I run my own company called Pragmatic Web Security, through which I help other companies build more secure software. That's essentially my niche, the thing I do. I do that through training. So I give them developer-specific security training, but I also consult with companies on things like API authentication, building out prototypes, helping them figure out the best way to approach their security challenges, so to speak. I'm a Google developer expert and an Auth0 ambassador, which are community outreach programs. So I'm not working for Google or Auth0. I'm just in their DevRel programs, and we regularly communicate and stuff like that. Just to make things clear, I'm not employed by any of these companies, or I don't financially benefit from them either. But enough about me. Let's talk about authentication. Client authentication. Let's start with basic client authentication. Actually, let's start. You know that image from before, the crappy lamb with the strawberry eyes? Like, seriously, I wish you could forget that, but you'll never be able to forget that one. But when you think of that image, remind yourself that it's kind of similar as just throwing a secret around in APIs. So one of the ways to authenticate a client to an API is just if both have a secret and you send that secret to the API, then the API can verify that. That's basically a string comparison. And when that turns out to be the same, then we consider that client to be authenticated. Very simple, very straightforward. If you put this on a slide, this probably doesn't seem like the bestest of ideas. It's like, sure, this can kind of work. It's very similar to using passwords, but for APIs. So yeah, let's talk about the properties. Well, first, let's talk about how to implement this. One common way to implement this is with basic auth. HTTP has this authentication mechanism built in since the early days, like literally the early 90s or even 80s. I'm not exactly sure when the first version of HTTP was built with HTTP basic auth, but it has been there for a long time. And when you use basic auth, the server or the client basically includes a header called the authorization header, which is very weird because it's about authentication, but sure. And it includes a type basic and then a seemingly random piece of junk. But that seemingly random piece of junk is just base64 encoding to make it URL safe. And base64 encoding can be easily decoded by anyone who has that string, and it will be a value consisting of username, password. So it's plain text credentials being sent on every request. And you can imagine back in the day, that was not over HTTPS. That was just over the web. So this is not a great mechanism. A little bit of a more modern incarnation of the same mechanism, just not part of the HTTP spec, would be the use of API keys. So the same setup is with API keys. It's a secret. That API key is often a secret that's just known by the client, sent on our attached to the request, sent to the API, and the API verifies that. And by itself, there's nothing wrong per se with API keys. They work and they have their valid applications, but they also have very important limitations. And that brings us to the first recipe card or overview slide. I can't do air quotes that much because I have a broken wrist on the other side, so I'll have to do with single side air quotes when I talk about things like this. But that aside, shared secrets, they work sort of. They work in very limited use cases. I've used them in scenarios because sometimes it's actually useful. And that brings us to the benefits here. So it's a lightweight mechanism with minimal overhead. So performance-wise, this is really good. I just wouldn't trust it as the only defense. I would suggest you can use this as kind of a first layer of defense. Like, hey, let's have an easy way to decide if a request is supposed to pass the perimeter or not before we even handle it internally with another authentication mechanism added on top. That might be a good way to implement this in practice. Definitely do not use this across trust zones without additional protection mechanisms in place. What are some of the biggest drawbacks of using shared secrets like this? Well, First of all, every party involved has to know the secret. So here, that's a client and an API, but imagine that there's like a reverse proxy in the middle, an Nginx proxying requests to internal APIs. Well, if that reverse proxy sees the traffic, it will see that secret as well. Maybe it already checks it. That would be a good first layer of defense. Maybe it doesn't, but it will see that secret. There's no way to avoid that. Scalability is a big issue here, because let's say you have 1,000 clients and 1,000 APIs. Well, I'm not a math wizard, but that's going to be a lot of combinations if every client has to authenticate to every API. So that's going to be a lot of pairs because, well, let's face it, if you all use the same secret, then there's not much authentication going on. It's just, oh yeah, you know the secret, you're one of those 1,000. I have no idea who you are. So your authorization decision is not going to be very accurate in that case. So you have a lot of secrets floating around, and the secret is not linked to the request in any way. That's maybe a very big drawback, because that means if somebody takes that secret from one request to get some information, they can slap it on a request to delete all data, and the API is like, oh yeah, you know the secret, you must be the legitimate client, and boom, all your data is gone. Well, you probably don't have an endpoint delete all, but you kind of get the idea here. So let's see if we can fix these drawbacks moving forward. Let's make our food a bit more delicious and a bit more fancy along the way. All right. What if we tackle that linking to the request first? What if we use that secret, and instead of just throwing the secret back and forth between the client and the API, we could use that secret to generate an HMAC. And an HMAC is a sort of signature. It's not really a signature precisely, but it's a cryptographic operation that is based on a piece of data. So the client can calculate that HMAC on the request and attach the HMAC to the request instead of the secret. And I'm going to explain how this works on the next slide in a little bit more detail. The API can use a verification procedure to ensure that this HMAC is indeed valid, linked to the request, generated with a secret, and that would give the API its authentication mechanism. How do you implement this? Well, there's a variety of ways. You could include this HMAC in a custom request header. You can call it whatever you want. For example, GitHub. I've been working with GitHub apps recently for a customer, and GitHub uses this to authenticate calls to a webhook. So you can configure GitHub with a secret, and they will calculate a signature over the payload of the request and add it in a custom header, which is a very long GitHub-specific header. But that's exactly this mechanism of authenticating a client to an API, GitHub to your API in that case. So why does this work? How does an HMAC work, and what are the properties we get here? Well, let me illustrate that with an image. Don't worry, no cryptographic mathematical details, just the security properties that are relevant for us developers. So the client uses an HMAC function. So you don't really write your own, you just use an HMAC function because cryptographic functions have very peculiar details that you need to get right. So with that HMAC function, you give it input. The input is the data of the request, which is something that you have to agree on. What do you put into that HMAC function? Well, in this case, some data from the request along with the secret. And that HMAC function spits out the HMAC, which is typically hex encoded because it's the output of a hash function. And that's the easiest way to represent that value. That's easy to handle in other systems as well. And that's the HMAC that we add into the request, for example, with that custom request header. Whenever the API has to validate that HMAC, it gets the request and the HMAC. The API will feed the request data and the secret into an HMAC function, the same HMAC function, and out comes another HMAC value. And now it's a matter of doing a string comparison, which you want to do in constant time, but that's, again, a detail. So you compare these two values, and if it's green, then you know that the inputs to the HMAC function at the bottom of the slide were the same as the inputs at the top of the slide, which means the request hasn't changed. The HMAC actually belongs to this request data, and it has been generated with the secret, the same secret as the API used. So this tells you that if the client is the only one with that secret in possession, that this request must have come from the client. If you end up in the red part, if the output is not the same, then something is different. Either the secret is different, the HMAC is wrong, or the request has been changed in between. We reject that request. That's essentially how this works in practice. And this is fairly lightweight and actually works quite well in practice. It works so well that this is used all over the place. I already mentioned GitHub as an example before. So GitHub is using this to authenticate calls on their webhooks, and Amazon is using that as well for internal calls to their IAM service and other services. So you can see here that in the AWS case, they have an authorization header with a custom type, which is AWS 4, signature version 4, basically, with an HMAC using the underlying SHA-256 hash function. And it includes a bunch of metadata to help the other party, the receiver, to verify that HMAC. So it says like, oh yeah, we included these headers into the request data, so you can actually include them as well, because the input has to be exactly the same for this mechanism to work. All right. There's another way to implement this. You could use a custom mechanism, which a lot of people are actually doing. So when I talk about API authentication in a training session, I would typically ask people first, like, what are you doing right now? And usually the answer is like, yeah, some API keys, some custom things, maybe this, maybe that. And one of the custom solutions typically relies on a JSON web token. And a JSON web token, I'll explain that in the next slide in a little bit more detail. But the JSON web token contains data and can be signed with an HMAC as well. So in that case, you would use that secret to sign that JSON web token, send that JSON web token to the API, which will verify that signature. And if everything checks out, the API is happy with that. And sending that can be done in a custom header, however you want to send that JSON web token, basically. Now, the reason that this kind of works well, and I actually often prefer using that, is because library support for JSON web tokens is really, really good. That means if you give me a language, I'll give you at least 3 JSON web token libraries for that language, because it's that widely supported, and that makes implementing something like this fairly easy if you know about the pitfalls of JSON web tokens, which I won't be able to talk about in this session, but you can find that session on YouTube if you want to. So what's a JSON web token? A JSON web token is basically a JSON-based data structure consisting of 3 parts, of which the first 2 are JSON objects, which are base64 encoded. So basically it looks like a token looks like the thing on the left without the colors. This is a decoding tool, but the actual contents are the stuff on the right. So you can see 2 JSON data structures and an HMAC signature in the blue part at the bottom. So it's base64 encoded, meaning that anybody can read that. It contains a set of claims. So whatever you want to put in a JSON web token, that's the payload, the purple part. And then it's integrity protected with a signature, which we can use to basically implement our client authentication mechanism with data integrity protection. And that's how to use an HMAC. So HMACs still rely on a shared secret, but they are linked to the request. That's essentially the overview of the overall. That's a drawback and a benefit all in one. So an HMAC provides integrity and authenticity to the data. That's really good. It's easy to implement, fairly easy to implement. It's used a lot in practice, by the way. And it basically works quite well because it's linked to a request. The drawbacks are that secret still has to be known by all involved parties. That's something we can't really avoid. That's something that we have to think about towards the future and see if we can fix that with other mechanisms. Because it affects scalability as well. That problem hasn't gone away. If you have a bunch of clients and a bunch of APIs, you'll need unique secret pairs for all client API combinations, especially if APIs call each other. It's going to get definitely a bit more messy. Which brings us right to the next section, advanced client authentication. All right. So where are we at now? What if we removed the need for shared secrets? That would make a lot of things a lot better rather quickly. So how do we do that? Well, by switching the underlying cryptographic mechanism to sign or to provide integrity or authenticity on the data. And instead of using a shared secret, we're going to use a public-private key pair. And that's basically a key pair that's linked together. When you generate them, you generate a private key, and from the private key, you generate a public key. And the public key is supposed to be public, as in nobody can do anything useful with the public key. That's basically what it means. So if I generate such a key pair, I can literally give all of you the public key without risking any security issues on my end. And whenever I want to sign something, I use my private key. So the client will use a private key to create a signature, and send that signature along with the request to the API. And the API knows like, oh, you're supposed to be client X. You know what? Let's verify that. Let's use the key of client X and verify that signature. And if that checks out, then, well, we're kind of assuming you're client X because you're the only one supposed to know that private key. And that's essentially how this works in practice. And this signature is sort of a proof of possession mechanism. In this context, you'll often find this described as proof of possession, which demonstrates that the client possesses the private key. And this works really well because the private key is only supposed to be known by one specific party. Like I said, I can give all of you my public key, but that private key is never supposed to leave my possession. So the only way to impersonate me would be to come to Belgium with a baseball bat, come to my house and beat me. Well, once is probably enough before I give you my private key, and then you can pretend to be me. But otherwise, there will be no feasible way to do that in practice. So how does that work behind the scenes? Well, again, there's cryptographic libraries for that. You have signing functions. RSA is probably the best known algorithm that does exactly a signature like this, but there are better alternatives available today, depending on what your libraries support, basically. The concept is very much the same as the HMAC concept. We feed data into that algorithm, request data, along with a private key, and out comes a signature, which is, again, encoded in base64 or hex or whatever works for you. And that signature and the data is what we send to the API. Big difference now, verification uses the public key, not the shared secret. So the API uses the public key, feeds that into a verification function because it's not a simple string comparison anymore. So you feed the data, the actual signature you received, and the public key into a verification function, and it spits out true or false, or exception, no exception, or whatever works for your language, basically. And the colors are very much the same as before. If it's green, it means that the data is the same, the signature is valid, and has been generated by the private key that belongs to this public key, which in our case means we are confident that this must have come from the legitimate client. Well, if the client's private key is compromised, then all bets are off, but that shouldn't happen in any circumstance. And red means something is different. Maybe the data changed, maybe the key is wrong. Well, we don't really care, actually. We just throw it out and be gone with that. That's essentially what this means in practice. All right. Sounds doable. How is this implemented or used in practice? How do you handle the details under the hood? Well, one mechanism is the use of HTTP signatures. So there's a spec that they're actually developing, which is called the HTTP signature specification, and it's defining something exactly like this. So it looks very similar to the Amazon AWS example. That's because the HTTP signature spec also supports HMACs, which is very much the same as Amazon's signature mechanism. So what do we have? Well, we have the request, we have a signature header, which contains all the metadata to recreate or to verify that signature on the receiving end. So it contains a key ID telling the API, like, you should use this specific key to verify the signature. It includes algorithm information, the headers that have been included, and so on and so on. All right. You can also implement this mechanism with a JSON Web Token. And that's also often done in practice. A very good example would be, we'll talk about that specific thing later. So sorry about that. So how do you do that with a JSON Web Token? Well, the same as before. You can sign the JSON Web Token with a private key. That's also well supported by every JOT library you can find. So you can sign it with a private key, and this API can verify that signature with the public key. So that's definitely one way to do that. And what I wanted to mention before is this is widely supported in the OAuth ecosystem. So OAuth, which I'll discuss in a little bit more detail later, but not too much because it's insanely complicated, is basically a framework to enable complex architectures where clients are accessing APIs as themselves or on behalf of users and something. But in essence, one of the specs in the OAuth landscape talks about how to use JSON Web Tokens for client authentication. So if you ever want to implement that, and that's a piece of advice I give to a lot of people, if you want to implement something like this with JSON Web Tokens, please look at that spec, RC7523, because these specs include a section called security considerations. As in, hey, these are a bunch of mistakes that people might make when building something like this, so please take this into account. So look at those sections of the spec to ensure that your mechanism is actually secure and covers these things in practice. And that brings us to another recipe card. So we have asymmetric request signatures. That's called asymmetric because it's not with a shared secret, but with a different key on both ends, hence the name asymmetric. But the client or the sender signs something with a private key, and the receiver verifies that with a public key. That's essentially what this means in practice. The benefits here are actually quite good. There's no shared secret. The only thing we need to share is the public key. So you have to configure the receiver like, yeah, this key belongs to that client, and that's it. If your API ever gets compromised, somebody steals the public keys, no biggie. Seriously, no problem at all. If somebody steals the private keys, big problem. Public keys, nobody cares. There's literally key registries online, by the way, with public keys from people if you want to send them an email and stuff like that. Works really well when a client relies on multiple APIs because the scalability thing is also covered now. One client, one private key, you give all your APIs, all 1,000 of them, the public key, and they can handle requests coming in from that client. So instead of having the need for these pairs of secrets, we only need one private key per client entity and then distribute the public keys amongst our APIs. Drawbacks. Well, once you start rolling this out, you'll quickly notice that key management and trustworthiness of a key is quite a challenge. It's not that hard, but it's something you have to think about and plan for. It's not something you can just drop keys in code and, well, you're not going to push out a code update to your APIs every time you have a new client and stuff like that. So you need to actually think about how to handle that upfront and make sure you get that right. Integrity protection is only applied on the signed data. So whatever data you include in the signature, that is protected. The rest is not. And there's also no confidentiality. And these drawbacks are not that important because you probably use TLS anyway. So you get confidentiality on the network and you get integrity of the data you send over the network. But I added them here because there's one very interesting aspect. And you can use this mechanism in combination with TLS or actually right in TLS itself. And that is something we call mutual TLS. And in a mutual TLS setup, we get the best of all worlds, basically. Except maybe certificate management, but that's a different story. So in an MTLS setup or mutual TLS, what we basically have is we have the client and the API, and both parties have a set of private public key pairs, or both parties have a private public key and corresponding certificates. And whenever we set up a connection, both parties will verify each other's certificates. So when a client connects to an API, it's going to use HTTPS, and there's probably going to be certificate validation in that step present already. But we also do it vice versa. We also do, the API also gets a certificate from the client and checks that the client has signed a challenge with its private key, which belongs to the public key, which is in the certificate. And that gives both of them the assurances that the other party is who they claim to be, along with confidentiality and integrity on the channel. That's essentially what MTLS brings to the table. And the best part of MTLS is that it's absolutely easy to implement and widely supported. So if you want to implement this in Node.js, it takes you literally one line of code to do that, because every TLS library that has been around for 10 or 15 years supports MTLS because it has been a part of TLS for a very long time. And the same thing in Java. If you want to set up MTLS out and Spring Boot APIs, it's a matter of configuration, setting I don't know the exact name of the property, but it's like a client's TLS needed. It's like, yeah, we need that, boom. And the TLS library will enforce the presence of a client certificate. You can rely on the information in that certificate to establish the identity of the client and make your authorization decisions, and so on and so on. So MTLS is actually highly recommended for any native application. So any application where you set up a TLS connection using, well, set it up from within your code, you can configure that TLS connection to use client certificates. Even self-signed certificates work if you know how to trust them. It doesn't work in a browser. That's the drawback. Browsers can do MTLS, but the interface is absolutely horrible. And the user will be prompted to select a certificate, and the user is going to be like, what the hell is a certificate? And you can see where this is going, right? So it doesn't really work well in browser-based settings. But it works really well in API to API communication. It works really well in native client to API communication, and so on and so on. All right. Where is this used in practice? Well, OAuth, that large and complex framework, actually has a spec, RFC 8705, that describes how to use MTLS for client authentication. So that's essentially a very good example of where this is used in practice. Again, look at the spec for security considerations and so on. But this has become the holy grail of client authentication in OAuth systems, and highly sensitive applications actually rely on MTLS for authentication in that setup. Other systems are moving in that direction as well. You have Amazon, for example, their API gateway now supports MTLS authentication as well, which is absolutely awesome, easy to configure, and easy to use in practice. And you'll find frameworks like an Istio that supports this out of the box without the need for any specific configuration. So there's Citadel component in the middle, issue certificates to containers, and you can specify access control policies based on the identities associated with these services. So service A would have its certificate, service B would have its certificate, and then MTLS is used on any connection between them. And you can specify like, yeah, A can talk to B, but B cannot talk to A, for example. That's essentially how this would work in practice. So whenever you can, I actually have an overview at the end of this presentation with all the techniques we talked about, but whenever you can, use MTLS for client authentication. All right. Let's talk about something completely different. What about user authentication? Well, one of the interesting things about client authentication is that we've been authenticating the client on every request. Whether we add an API key or we add a signature on every incoming request, the API will be like, let's verify who you are. Oh, you are client X. Everything checks out. Awesome. Let's handle that request. Guess what that means for a user? Users don't want to enter their password every single time you send a request. So user authentication only happens once. In a user authentication scenario, you would get something like this. The user would use, they use a front-end application, in this case, a web app. It can also be something else, but regardless, in any type of client, the user, in this case, provides credentials to the application, which authenticates once with a service. Whether that's a separate service or a component in your application doesn't matter. In this case, the client is a web application, and this service decides to use cookies to track authenticated state. That's a key property of user authentication. We authenticate once, and then we track authenticated state, which we call session management, whether it's with cookies or a token mechanism or whatever. We track that state across requests. So we authenticate once in step 1 and 2, and from that point on, whatever the client application, the front-end web app, sends to the API will carry some state about who the authenticated user is, allowing the API to make its authorization decisions. That's a massive change in the approach to authentication. So instead of doing it every request, we do it once, and then we track it for X amount of time, which can be 10 minutes, 8 hours, whatever you see fit, basically. And how the user authenticates is completely independent from how you track that authentication state. So in the context of APIs, we don't really care about user authentication per se, because as we said in the beginning, the API doesn't really care about authentication. It cares about authorization. And that's the key component here. So when the API knows who the authenticated user is, it can make an informed authentication decision. And you get a response, of course. This cookie works well when you have a client, a web client, and API running in the same domain. So if everything runs in the same domain, you have an app.restofgate.com and your API is running on /API in that same domain, this will work really well and is actually the easiest way to implement state tracking for web applications. Keep in mind that this doesn't mean that you have to use a stateful backend with server-side sessions. You'll also find cookie libraries that track sessions on the client, which also has some benefits, even though the benefits quickly erode from in those use cases. So benefits, cookies are handled automatically by the browser. That's definitely a good thing. It's supported by most backend frameworks. So if you're building a small scale application, if you know you'll never have more than a couple of hundred users, then this is actually the easiest way to set up state tracking in web applications. Drawbacks: cookies work well in browsers, but not anywhere else, and only within a single domain. That's definitely a limitation. And it also, there's a very big danger that if you suggest the use of cookies, that people will laugh at you, because the cool kids building single page JavaScript applications think that cookies are for old timers doing backend PHP apps or whatever, which is absolutely not true, by the way. That's a big load of bullcrap, but sure. So what are the cool kids doing? Well, the cool kids are doing token-based auth. And token-based auth is a very meaningless concept. That's kind of weird, but the concept is very similar as the previous one. So you basically have a user providing the client with credentials, and the client goes to an authentication service, just like before. And instead of getting a cookie with some information, we get a token, a JSON web token typically. And that token is what we attach on request to the API. The API will verify that token and use that token for authorization and send a response back to the client. That's essentially the setup. What does that look like? Well, something like this. Seriously, look for the concept token-based authentication, and you'll find hundreds of blog posts detailing exactly this type of setup. And there's a whole bunch of drawbacks, because these drawbacks are very similar to the use of client-side cookies, by the way, because putting information in a token that's not controlled by any server is definitely going to cause problems in case you run into the need for revocation, or if you want to manage active sessions or something like that. So this concept has been taken from larger ecosystems like OAuth, which I'll talk about in the final part of this presentation. From larger ecosystems like OAuth, they added this one specific concept, which seems to work great in small scale scenarios, but quickly runs into challenges once you reach a larger scale. This is token-based authentication. Again, air quotes, because it's not really authentication, but state propagation. So we're tracking authentication state in a token. And the client sends a token on every request to the API. Benefits: well, there are some benefits. So this works really well for all types of clients, mobile or web, doesn't matter, because you can easily add that token in a header. Works well within within a single application. Might be a bit challenging if you have multiple applications, where you want to implement something like single sign-on. So what are the drawbacks? Well, there's a lot of custom code to make this work. Nowadays, things are getting better, so you'll find some frameworks that have support for this out of the box, but other frameworks where you have like 5 cookie libraries to choose from will require you to handle your tokens yourself. Long-lived tokens are definitely dangerous, so you'll see tokens flying around that are valid for 12 hours, 2 days, where there's no recourse if one of those tokens gets stolen. And securing these tokens in the browser is really, really hard. If something goes wrong in your browser-based application, if some malicious JavaScript executes, it's very easy to extract tokens, while it may be a bit harder to extract cookies. That's, of course, only a side effect. You should avoid the execution of malicious code in the first place, but you kind of get the idea of the challenges here. I'm fairly brief here for a specific reason. That's because both previous approaches, in my opinion, are becoming less and less relevant in a world where we have OAuth and OpenID Connect. OAuth and OpenID Connect are somewhat more complicated technologies where we rely on a central party to handle user authentication and to issue tokens. That's essentially what this really comes down to. So how would that work in practice? Very briefly, by the way, because I really can't go into any details because of time constraints. We would need 2 days to flesh this out in detail. So the client starts an OAuth flow. And an OAuth flow is basically a way to interact, or to have the user interact with this authorization server, this central concept. And the authorization server is going to ask the user to authenticate. So that's a main difference here, is that the client doesn't have to handle credentials anymore. The user will log in through a web interface of the authorization server without the need for the client to handle any credentials. The authorization server responds with an access token, and the client can use that access token to send requests to the API, which will use that token for authorization. And this combines both approaches that we discussed before, because on step 2 and 3, the browser of the user and the authorization server will rely on cookies. Step 4 issues a token, which is then used in step 5 for authorizing a request. And typically between the client and the authorization server, we implement some form of client authentication if that is a backend web application. So this is actually a combination of all technologies together. All right. So that's what OAuth brings to the table. Benefits of this approach: OpenID Connect on top of this does user authentication, by the way, which is not too relevant for the API, but might be relevant for the client application. The benefit of this approach is that we get things like single sign-on, token management. We can revoke access by going to the authorization server and say, like, yeah, I don't want this client accessing my stuff anymore, and so on and so on. And this is the de facto standard to implement distributed authorization and somewhat authentication scenarios these days. You've all been using this, by the way. If you, for example, if you use an app that can put things in your Google Calendar, you might encounter the fact that you have to log in with Google first and then approve an application to access your stuff at Google. That's this protocol at work. The API would be Google's Calendar API, and the authorization server would be Google's authorization server in that case. An OAuth access token is a JSON web token, a bit longer than the one I showed you before because there's a lot more data in there. And that JSON web token contains a bunch of claims about who the user is. So I actually have a slide on this. So it contains the SUB claim, and that identifies the user within that issuer. So basically, it tells the API the identifier of the user is this value. So the API will be able to use that value to say, like, oh yeah, I know that guy. That's Philippe. Awesome. We have the AZP claim, which is the authorized party. That's the client for which this token was issued. So the API can now say, like, oh, the user is Philippe and the client is this retrograde web application. Like, yeah, I allow that one to read reviews, for example. There's an audience. You can restrict tokens to a specific audience who's supposed to use that token. That's the AUD claim. And there's an expiration built into that as well. There's a whole lot more, but we'll talk about. So we'll not talk about this here, but I'll talk about that in other places. So OAuth access tokens, the benefits are basically that it's a uniform authorization framework for various clients, supports authorization supports the delegation of authority, so a client can act on behalf of a user, but it also supports machine-to-machine authentication and stuff like that. OAuth is a very well-defined framework. There's a lot of research on OAuth, a lot of work on making this secure, so you get all of that out of the box, basically. That's good. The drawbacks is it's very complex to understand. So you'll need to spend quite a bit of time actually understanding how OAuth is supposed to work and what it does in practice before you can actually do this or implement this in your architecture. And most of my consulting work these days focuses on implementing OAuth and OIDC and stuff like that. Also, because I'm sort of specialized in that, I have an online course, a very detailed online course that dives deeper into how to work with OAuth and OpenID Connect and what it means. There's a free part. So the first module is free. So if you want to know more, definitely take that free module. And if you want to dig deeper, there's 2 follow-up modules that are paid that go into a lot more details. All right, I promised you an overview, so here we go. Let me briefly walk through that overview to wrap up this presentation. We talked about shared secrets. Simple mechanism. I would say it works kind of well in a single trust zone. I would use that as a first line of defense, as a simple string-based checking mechanism that you can use in combination with more complex signature-based solutions. So asymmetric request signatures work really well as well. So you can combine, for example, an API key with a signed JSON web token. That would be a solid way to authenticate a client to an API. MTLS is actually recommended for service-to-service communication, especially direct communication, and also for all native clients. And then on the user authentication side, we have cookie-based auth, which is actually my recommendation for web application architectures where you don't have other types of applications if you can make it work within your domain. Token-based auth is not recommended without some revocation mechanism, which really quickly leads you to rebuilding OAuth in practice. So my recommendation today would be to move towards OAuth access tokens, because that's going to be the most elaborate mechanism, and it's going to future-proof your applications. All right. To wrap things up, you can find the slides on my website, by the way. Here's a bunch of references to the specs I mentioned in one single overview. And with that, I want to thank you for watching. You can connect with me on social media to stay up to date on security content and courses and presentations and stuff like that. And that leaves a couple of minutes for a Q&A. So if you have any questions, drop them in the Q&A, and I'll do my best of answering a couple of them right now. Thanks for being here. All right, so one of the questions is about user authentication in a stateless application. Well, honestly, it depends what you call a stateless app, but user authentication is typically the means to an end, the means to, and the end is authorization. So my recommendation would be to use an identity provider in combination with OAuth and OpenID Connect, because that's basically going to offload all the hard parts to someone else. So if you use Auth0, for example, like I do for my application, it means that they handle authentication, they handle user management, reset passwords, the email flow, and all of that stuff. I don't have to worry about any of that. So all I do is I call them, I send the user to Auth0, and in the end, I get an identity token, which tells me exactly the user has this identifier. Here's the name of the user if they entered that, and an email address, and so on and so on. And then the client, my application would also get an access token, which I can use to call my APIs. And my API can then be like, oh yeah, it's this user with that ID. Awesome. And from that point on, we have our API authentication mechanism implemented. So that would be the recommendation here. If you have any other questions, I can see you're giving thumbs up to existing questions. So if there's anything else, don't hesitate to ask me right now. If you think of something later, there's also a security panel tomorrow morning where I'm going to be along with a couple of other speakers. So you can also join us there and harass us about anything security related. All right. With that, thank you for being here, and maybe I'll see you tomorrow in the security panel. Bye-bye.